Yeah, good evening, students. My voice is audible, right?
Three ready for 4 ready to yeah.
Sir, I made you as a host. You can start the session, sir.
Okay, fine. I'm just waiting for your response only.
Yeah, okay, sir. Fine, no problem. You can start the session, sir.
Okay, guys. Just a second, please. Yeah. Hello, students. Good evening. Hope. Coming to myself. I'm audible, right? Clearly?
Yes, sir. Clear.
Yeah.
Yes, sir.
Is there any fluctuations in my voice?
No, sir.
It's fine, right?
Yes,
Yes, sir. Yes, sir.
Okay, let's get first comfortable to each other. Okay, as we are hardly, I can see on 7 students or 6 or 8, right? So let us first get compatible with each other in the terms of our structural analysis, and then we'll go slowly. Okay, and coming to this subject, let us say, as Vinod sir already told me that I think you guys have already taken this course, and let's just start this again freshly. Okay. Let me share my screen first of all, and then we'll discuss. And is it visible, my screen?
Yes, sir. Visible, sir.
Okay, see, as you can see in my slide, it's all are completely blank pages, right? As you can see. So
Yes, sir. Yes, sir.
let's take this as a discussion kind of a thing. Okay. We are not going to discuss anything new, or I'm not strictly talking about our whatever our complete course study kind of thing. Before that, let me just guide you through the syllabus. Okay. So this is what the syllabus I have taken screenshot from the GATE 2023 website. As you can see here, just a second. Okay, you might have gone through this syllabus. So see, it is simply from syllabus, it will be seen like only 3 lines or 4 lines. But as I can say, in these 4 lines, they have completely incorporated whatever the things that we have learned in our regular courses. SA1, SA2, I don't know. For somebody, it is indeterminate structural analysis or so on. So if we first go through briefly about the syllabus of this course, as you can see, there are 2 primary topics. So those are nothing but determinate and indeterminate structures, right? From the name itself, we can understand, yeah, determinate, right? We can get a sense of meaning. And indeterminate, it doesn't mean that they will be indeterminate, complete our or at the end of the solution. Definitely they are going to be determinate, but we will see what will happen or what is the difference between these two. And they said like we have to use either force methods or energy methods. You might have gone through them in your courses, or we will again discuss all these things in detail. So we have to study about trusses, we have to study about arches, beams, cables, frames. So tell me, have you guys studied anything other than about these 5 types of structures in your regular course? I don't think you will, right? Trusses, arches, beams, cables, and frames. And these are all just methods, like whether you're talking about, see here, displacement method type you are kind of using, or you are using the energy type of kind of thing, or you are using the, like, these are some other methods like flexibility method or stiffness method. Okay. So the main introduction that we will start from today is that we will start it from what is determinate, and we will start it from what is indeterminate. Okay. Before going to discuss about it, first of all, let me tell you at what stage I am during my BTech or during the course of me, like when I'm taking structural analysis course in my BTech. Let me tell you what example my teacher has gave me. She has simply given this problem, and you know what she just asked me? She asked me to take a section XX. Don't think I am going into these details. I'm just explaining you my situation during my BTech course. Let us say the load is P and the distance for the section is X. Can you guys tell me what is the moment at that section XX? Forget about the sign, whether it is positive or negative, doesn't matter. What about this moment at this section XX? You guys mostly know, right? P into X. But you know what I have told her? Let's say she is also given her length of the cantilever beam is L. What I told her, you know? I told her that only I know that P into L, that's it. So you can see both are same, isn't it? P into L or P into X. If in the place of X, I can place L. That's also the right answer. But at that stage, I'm not even able to answer this P into X. Why? Because at that stage, we might not have so many, or we don't have any kind of basic things. And that's why we may not incorporate these things. And then we can't able to express. So the first thing in analysis is that no need to by heart any formulas, nothing at all. You should, but if I compare with other subjects, I can say these will be barely minimum formulas that you have to remember. Agree or not? Or do we have to by heart so many formulas, just like kind of say geotechnical engineering? Do we have to? My answer is no. Right? So if we are talking about analysis course, not only here, if you take GATE or if you take engineering services, or if you take any state or PSUs exams. So the first thing that we have to learn from this is that we should know the application. I know the formula, summation of x equal to 0, fy equal to 0, summation my equal to 0. But by using those equations, at what extent I can apply in the real kind of problems, or what are the problems that we get in the exams. Obviously, frankly, I will tell you, without these equations, there is no problem that we can solve in this course. Or I can blindly say only you have to use summation of x equal to 0, fy 0, or summation of moments equal to 0. If it is a 2D problem. So the whole heart of this analysis is lying in those 3 equations only. I can guarantee say that if it is a 2D problem. But where we are facing these problems, that step by step we will improve them. Okay. So before that, so let us discuss some formal kind of questions. Again, I'm telling you nothing to do with the directly nothing to do with the our analysis course. Okay. Let me take this is kind of plane I'm talking to. I'm not writing any object. Okay. Let us say I'm talking about some plane. Let us say I'm talking about the plane X. I'm talking about the plane. So I'm talking about the XY plane like that. Two other planes also I can write it, isn't it? If I'm talking about two-dimensional problems, obviously we have 2 dimensions. Either I can have XY. What else I can have? I can have YZ plane. Or what is the other plane that we can have? XZ plane, right? I request, as we are not discussing any hard kind of problems, or we have not kindly gone through the typical problematic types. So kindly can you please respond? And one more thing is that if you guys are not understanding, please stop me. In the first 2 lectures or first 4 lectures, we are going to discuss very basic things. As I'm telling you, as these are very basic things, these are the heart of the problems. If you are not understood these problems, then it will be difficult for applying into the real problems. Do you guys agree that if I'm talking about the 2-dimensional plane, I can write, or I can talk about XY plane, I can talk about YZ plane, I can talk about XZ plane. Is it right? Or any other plane I can represent? Any other plane is possible?
No, sir.
No, right? Just we have taken X, Y, Y, Z, and ZX, 3 different planes, right? So let us assume that, let us say, I'm talking about now XY plane only. Once again, I'm insisting that I'm at this stage, it is not hardly required to talk about XY plane specifically. But if you are talking about, or if you always imagine the things with respect to some specific axis, then further it will be very much clearer for us how the things we are going to imagine or how the things we are going to apply. Okay. So now I am talking about the XY plane only. Okay. And this is what my plane boundary, as you can see here. And let us say that I have taken a scale, just normal rural scale that we use in our day-to-day life. Imagine either it can be of wood or steel or plastic, anything. Let us say this is a scale. Let us say it is having a length L. Okay. Now tell me in how many ways this scale can move in this plane. That means if I'm talking about XY plane, or you can imagine that there is a scale, I kept it on the table, and the axis of the table is, top surface of the table is XY. So if I kept a scale on the table, can you tell me in how many ways I can move this scale?
2 ways, sir.
How many ways?
2, sir.
2 or 3? What is the answer?
2, sir. 2.
2. Anybody is going for 3? So if I'm talking about the movement of the scale, right?
Sir.
As you can say, I can move this along which direction? X direction, isn't it? That means initially the scale is like this, or after some point of time, the scale might be here. That means it has moved along X direction, isn't it? Similarly, it might move along Y direction. And there is also one more possibility, right? What is it if you speak about? These two are nothing but movement along x direction, or I can say movement along y direction. What is one more possibility? Instead of moving along x and y, the scale position won't change. The central position of the scale won't change. But what will happen? It will simply rotate with respect to some reference point, isn't it? So if you are talking about a 2D plane, if I'm talking about strictly about XY plane, so if I take any object, how many motions are possible? It can move along X, it can move along Y, and what about the another motion?
XY.
Rotation, isn't it?
Yes, sir. Theta X.
So generally we will represent with displacements or movements as delta X and delta Y. How we will represent the rotations?
Theta, sir.
Theta, isn't it? So what is theta? Like, see, if I'm talking about the displacements or movements, see, I'm talking about delta X, I'm talking about delta Y. What about the direction of this rotation? Is it X? Is it Y? Is it Z? How do we have to represent it?
Is it?
Z, right? So always rotation we will represent with respect to the perpendicular to the axis. You might have imagined, right, the right hand thumb rule or whatever it may be. So here I have to, if it is a rotation, I have to represent with respect to, always with respect to the perpendicular to the plane. So here I can say theta Z, isn't it? So tell me, is there any doubt in these three? So if I'm talking about a two-dimensional plane, so if I'm taking any object, either it will move in, the movement it can be in X or it can be Y, and rotation also it can be Z. So similarly tell me, what about if I'm talking about YZ plane? So if I'm taking an object in YZ plane, what are the possible kind of motions that we can predict? How many motions we can predict? If I'm talking about two-dimensional YZ plane, how many we can predict? Just like the same thing, just like you have said about XY, similarly.
3, sir.
So 3, what are those 3?
Oh, translation and rotation.
Always please be specific with the direction because it will be help us a lot. So here it can move along Y, it can move along Z, and also what about the rotation? What is the direction of the rotation?
Theta X, sir.
Theta X, right? Similarly, if I'm talking about ZX plane, what is the movement along X direction? Delta X, movement along Z direction, delta Z, and about the rotation is with respect to
Theta Y.
theta Y, right? So initially we have started with 2D plane, XY we have discussed separately, YZ we have discussed separately, ZX we have discussed separately, right? Now, if I'm talking about 3D plane, if it is a 3D plane, in general, we are representing with X, Y, Z. Now tell me how many motions are possible. Previously, we have separated 3 planes separately. If it is XY, 3 are possible. YZ, 3 motions are possible. ZX, 3 motions are possible. If I combine them, it's kind of obvious, isn't it?
Yes, sir.
3 2D planes will exist. For each plane, 3 motions will be possible. So total, how many?
9.
Is it right? So here the movement along X direction, movement along Y direction, movement along Z direction. Similarly, rotation along X direction, rotation along Y direction, rotation along Z direction. So if you are talking about a 3D plane, total 6 possible motions will be there. Is it clear now? If I'm talking about 2D plane, three motions will be possible. If I'm talking about 3D plane or 3D object, there are 6 possible motions, right? As of now, I think it is clear, right? About the coordinate system. And let us say if I'm talking about 1D plane, sorry, I forgot to tell you. What happens if it is a 1D plane? If it is a 1D plane, we will represent with how?
Only one.
Only
We will
one
represent with
direction.
either X direction, we will represent either with Y, or we will represent with Z, isn't it? So there
Yes,
is only one possible motion, that is either with respect to X, with respect to Y, or with respect to Z. Okay, those who have already clarity on these things, please don't get bored, because these are the basics to start with. And these are very, very, very important, because of these things only we are going to find out our static indeterminacy or kinematic indeterminacy. So that's why we are discussing them in detail. Okay. I am getting one more thing, or you might have discussed in our regular kind of thing, is that there are two possible motions that you guys are usually discussed in your regular courses, that is rigid body or deflected bodies, or we can say solid bodies. What is the difference between rigid body motion, or what is mean by a rigid body motion? What does this name implies? Rigid. So to whom people we call them as a rigid?
So fixed body.
Sorry, you are not clear. Let us say I have taken a stone. Imagine I have taken a stone, I have thrown it somewhere. Now tell me, do you really think that the stone dimensions are changing, or whether it is compressed, or whether the size of the stone is increased, volume is increased or decreased? Will it happen to the stone, or what will happen? It will move from, it will move from one place to the another place, isn't it? Initially, if I'm throwing from reference point, and it might go somewhere here. So if it is a rigid body motion, means what will happen? There won't be any volumetric changes to the object, or there won't be any strains. Those are possible in the motion. What will happen is that the body simply moves away from one place to another place. Just say that at point of time I'm sitting at one place, and after some point of time I have moved to somewhere. That means I'm changing the position. Just like the same thing, if I'm talking about rigid motion, the position of the object is changing from one place to the another place. That's it. You can see the best example. Suppose if I'm talking about a trolley or anything, if I push from one side, what will happen? It will move from one place to the another place, isn't it? So if I want to discuss about the final position of this object, I can say that it has displaced by a amount delta, isn't it?
Yes,
So this is the just basic thing. Or yeah, rigid body means just imagine that the position of this object is changing from one place to the another place. The best example for deflected bodies are like, if you're taking a rubber kind of thing, or if you are taking any elastic. So if you apply the force, what will happen? They will stretch and they will come back to original position. Or the best examples are like real life structures. Okay. So, and one more thing is that, what is the difference between the applied loads and resisted loads? Or I can say that, what is the difference between applied loads and the internal loads? What do you think? These two will be same, or these two will be different?
different.
Different.
The name itself, applied load, that means externally we are applying some forces on the objects. And what about internal load? Again, I'm taking the best example. Yeah. Let us say I have taken this object. Let us say these are frictionless. And if I apply some force like here, can you tell me what is the applied force? And can you tell me what is the internal force? Applied force, I know that you guys will say it directly. What is the applied force?
Yes.
F, right? What about the internal force?
Minus it. Opposite.
Is it F or is it 0? Which is right? What is the internal force?
Minus.
Hari said 0. Sorry, whoever is speaking, I don't know whose network issue is that. I could not able to hear properly. I think you can comment on the type session. Or you can just raise the hands. Who agrees with 0? Yeah, Ramesh said minus F. Okay, and any other thing? Any other guys? Let me see the majority. Ramya minus F, Anita minus F. Zero. Okay, let me tell you a best example. Okay. Let us say, yeah, 0. Most of them are 0, but let us discuss in detail. Okay. Let us say, suppose you are asking me to leave this class right now. Let us kind of assume that we have to take the permission if you want to leave. Okay. Suppose if you are asking me, sir, can I leave? If I say no, what you will just do? You will simply leave from the meeting. If I say no, what you will do? You will just stay in the meeting, isn't it? So, if I am allowing you to freely go away, obviously you will walk away. So, the first thing you have to understand here is that whether the resisting forces are developing in the systems or not. If there is no resisting force are developing, the synonym is like internal forces only. If you're freely or if the object can move freely, then you can say that no internal forces will develop in the system. That means in this case, if I apply the force like this, what will happen? Without showing any resistance, what will it do? It will simply move from its position. So the first thing you have to understand whether if you are applying a force, first you have to see whether it is trying to move away without resisting any force. That you have to observe him. So here in this case, as it will not develop any resisting, it will simply walk away from its position. So in this case, I can say that the internal force is equal to 0. So always remember, if the object is free to move away, no internal forces or no resisting forces will be developed. That means the main important that point you have to see is that if you're talking about any object, if the object is free to move. So this is very, very, very important thing. Not only here, even in the further problems, we will get to know them. If the object is free to move away along the direction of the force, then no internal forces will develop. So let me come back to the previous problem. Let us say I'm talking about two-dimensional plane, X, Y. Again, the same kind of thing. If I'm talking about an object, if I apply a force along X direction, then what will happen to this object? Let us say the objects are like this. Because of the application of the force, what will happen? See, as you can see the rollers here, just like you can imagine, skating boots you might have heard, right? So imagine that you are standing on the skating boots. And if someone pushes, so what will happen? You just simply move along the direction of the force, right? Just like the same thing, here the deflection or displacements can happen along the x direction. Similarly, if I apply the force along y direction, then the kind of motion can happen along the y direction. What about rotation? If I want my object to rotate, then which type of force I should apply? If it is a displacements, we can say it is a force. What about if it is a rotation? You have to apply movement along the z direction, as we are talking about specific plane. So if you want to apply a rotation, or if you want rotation to happen, you have to apply the movement. So what are the three parallel things? So if you are applying a force, deflection might be possible along x. If you are applying force along y, deflection or movement, anything along y direction. If you apply the moment along z, that's what we represent the moment. So the rotation will be possible along the z direction, right? Now, let me talk about, or let me come to this standard problem, that is simply supported problem. Let us say, if I am talking about like this. So here I am talking about the two-dimensional problems, okay? So what we'll call it as? It is a beam or bar? It is a beam problem, isn't it? I think you guys will remember, if it is a beam, it will resist the shear forces and also it will resist the bending moment. If it is a bar, it will resist only the axial forces. We'll discuss all these things in due time clearly. Okay. Now, as I'm talking about two-dimensional problem, in general, let us say if I take any point here, somewhere here, if I take any point somewhere here, can you tell me how many possible motions are possible at this point? Let us say if I'm talking about point P. And similarly, if I'm talking about my 2D plane is XY. If I talk about the point P, how many types of deflections are possible? Just like the same thing we have discussed previously. If it is a 2D plane, how many are possible? In general, forget about the loading and everything. Now I am talking about the two-dimensional problem. I am considering a point in the two-dimensional problem and how many displacements can be possible. Just, and second I'm saying, don't completely stick to this. Forget about this. This is just, I want to tell you that it is a beam problem. Now my question is, this is a two-dimensional problem, or I'm taking an object. I'm treating this simply supported beam as my object. I have taken an object in two-dimensional plane. In that object, I have taken, or I'm talking about a point P. Then how many types of deflections or how many types of movements are possible? We have discussed already.
Yes, sir.
It can be along x direction, it can be along y direction, and also it will be rotation. Completely forgot about the type of loading and everything. Now we are talking about only two-dimensional plane. If I'm talking about a point, at that point, there might be a deflection along x, deflection along y, and also there will be a rotation theta z, right? Now, let us say now we are talking about the hinge joint. I think you guys might know, right? How many reactions are possible at the hinge joint? What are they? Here it is, we will say that
horizontal and
horizontal and vertical. But let us say this is only possible if your plane is XY. What if my hinge support is like this? Will you say X and Y? Is it same? Is it right?
No, sir.
No, sir.
Then
No.
what is the better way or best way to say about type of force that a hinge on? Always you have to talk about parallel to the surface and perpendicular to the surface. So if I'm talking about this surface, see, if I'm talking about the surface of the hinge joint, I can say one force that might be parallel to this surface and one force that will be perpendicular to this surface. Similarly, if I want to represent for this, I will represent a force that is parallel to this surface and I will represent a force that is
Normal.
perpendicular to the surface, right? So if somebody asks you, even in interviews in further, you should always say that parallel to the surface or perpendicular to the surface, right? Now, the next point I will ask you is that, so these are resisting forces, I will say. Whatever the support reactions you are getting, those are resisting. The name itself you can understand, they are resisting something. So I can say two vice versa components, forces and deflection. Okay. If you apply the force, what will happen? Because of the application of the forces, deflections are possible, isn't it? So this is what we can say, these are nothing but applied forces. If you externally apply the forces, because of those external forces, deflections are possible. Then how about reaction forces? When they will develop? If you apply some forces externally, deflections are happen. When the reaction forces will develop? When the reaction will develop from us? If anybody stop us from doing something, then only the resistance will develop, isn't it? Whenever someone, not only in objects or mechanics or any body or even in us, if I stop asking you to do something, then obviously the reaction will develop from you, from anybody. So if you apply the forces, displacement will happen. If you don't want deflections to happen, how you will control them? If you don't want the deflection to be happen at one point, how you can control it? We have to resist it. How we will resist it? In the form of resisting forces. Is it clear? So if you apply the external forces, deflections are possible. If you don't want the deflections, resisting forces will act. So these are always vice versa kind of thing. If one happens, another will come into the picture. So let us say that there is a cantilever beam. If I am applying the force P, forget about rotation kind of thing. I'm not going to talk about rotation in this case. If you apply the force P, then what will happen? This will call it as a free end, isn't it? So because of this applied force, then what will happen? Deflections will happen, isn't it? Right? If you apply some external magnitude P, deflections will happen, that a magnitude is delta. Now somebody will come and say that I don't want any deflection at that point. My P will act like there only, but somebody comes and tells that I don't want any deflection. Then how can I restrict it? How can you stop? What mechanism you will apply at this point such that you should not have any deflection? That you guys know. If I don't want deflection, I will apply some resisting force opposite to that direction. So here the deflection is happening in the downward direction. If I don't want that amount, then what I can do? I can apply some resisting forces opposite to the direction of the deflection. So if I don't want any downward deflection, what I should do? I should apply a resisting force in the opposite direction along that point. So here I can say that my P is applied force and my F is the reaction force. Is it clear? The difference between the applied forces and the reaction forces? Now let us talk about types of supports. So now, even though it is not a support, now let us first discuss on the left hand side. Let us say I am talking about the structures that we are analyzing in two-dimensional plane. On the another side, I am talking about the structures that are analyzing in three-dimensional plane. You guys will agree, right? Drawing dimensions in 2D and 3D, that might be difficult. So I'm just telling you two-dimensional and three-dimensional. Okay. Now let us say the first and foremost in any class that we will discuss is pin joint, or we'll talk about hinge joint. So how we are going to represent it? This is what general kind of representation. So if it is a hinge joint or if it is a pin joint, how many reaction forces will develop? Here I'm not talking about the applied, I'm talking about the reaction forces. So first of all, I can ask you, why the reaction forces are developing at this point? Let us say if I'm talking about the plane XY. Can you tell me what are the reactions that are possible? Forget about the direction right now. Upward, downward, left side, that we'll discuss in detail. There might be reaction force that will develop along XY direction. And also there will be a reaction force that will develop along X direction. First of all, tell me why the reaction force along X direction is developing here.
Translation.
So what this hinge support is doing is that it will not allow any deflections along the X direction. How it will not allow the deflections? By applying the resisting forces. So at this point, it will not allow any deflection along the X direction. That's why the resisting force is developing, forgetting about in which direction the deflection is happening. Okay. So here, similarly, this hinge support will not allow any deflection along the Y direction. So that's why the resisting force is developing along the Y direction. So if somebody asks you about the pin joint or hinge joint, you should say that at the hinge connection, it will not allow any deflections along the X direction. It will not allow any deflections along Y direction. That's why resisting forces are developing along the corresponding directions. Okay. Suppose, let us say, this is what your beam. If the deflections are trying to happen along the right side direction, let us say this is what your x-axis, this is what your y. If the deflections are trying to happen along the positive x direction, what will be the reaction force direction? This is what your member and this is what your support. Imagine that at this point, this member will try to rotate or will try to translate along X direction or along the positive X direction. What will be the direction of the reaction force? Will it be on the right side or will it be on the left side?
Left, sir.
So here at this point, the beam or the object is trying to move along the right side direction. So to oppose the motion, the resisting force will develop always in the opposite direction. Similarly, if the deflection is happening in the upward direction, then the resisting force will develop in the downward direction. Why we are discussing these things is that while we are discussing about while solving the real type of problems, we might get confused with respect to whether it will be a positive f or positive y, negative x. Those kind of things will not disturb us, should not disturb us. That's why the direction of the force is that they will be always opposite to the direction of the movement. That's it. If rotation is happening in the clockwise direction, what will be the resisting movement then? Resisting movement will be in the anti-clockwise direction, right? Similarly, if I'm talking about the three-dimensional object, let us say I'm trying to draw this somewhere. Imagine this is a 3D object. Here also it is a hinge joint. If it is a hinge joint in three-dimensional plane, first of all, what you have to see, in how many directions the deflections, it will restrict the deflections. It won't allow any translations. It won't allow any X. It won't allow any translations along Y, and it won't allow any translations along Z. That means how many reaction forces will develop if you are solving it in a three-dimensional object. How many? If it is a 2D, two types of deformations are possible, either along X or Y. That's why resisting force along X and Y. If you are talking about three-dimensional plane, how many deflections are possible? Delta X is possible, delta Y is possible, delta Z is possible. So that's why how many resisting forces will develop? Resisting force along X is possible, resisting force along Y is possible, and also resisting force along Z is possible. Now this is what about hinge connection in two-dimensional and three-dimensional. Any doubt in this case? It's clear, right? Yeah, okay. Then, and another kind of support that we will see is a, what is the kind of support? Roller. So how we will generally represent the roller support? This means that it is continuous, okay? Imagine that if I place this object along X and Y. Now tell me, what is the difference between these two? The hinge connection and roller connection. You can see in which direction I have placed along the rollers. Rollers are placed along which direction? Along X direction, or they are placed along Y direction? They are placed along the X direction. That means if I am talking about this point, it can freely move, right? If I am talking about this point, or if let us say if I'm talking about point A, that point can freely move along X direction. That's why, as it can freely move along the direction, will there any resisting force develops along the direction? No. So, if any object or if any point, if it can freely move along one particular direction, then resisting forces will not develop. So here, as the rollers are placed along the X direction, along the direction as it can freely move, resisting forces will not develop along the X direction. What about Y? So roller support means it will always resist the displacement perpendicular to the surface. So if we're talking about the roller support, that will not allow any translation or displacements perpendicular to the surface of the support. What is the surface here? The surface of the roller support is, I am considering as truly horizontal. So it will not, what is the perpendicular direction to the surface? In this case, it is Y. So it will not allow any displacements along the Y direction. That's why resisting forces will develop only along the y direction. Suppose in the same case, if I draw a roller support like this, can you tell me in which direction forces will develop here? In this case, in which direction the forces will develop? Along x or y?
Y, sir.
Why?
Why?
Along X, along X.
So the problem why I am talking about planes is that, see, what is the directions of the planes I am considering? Y, X. What we have discussed, if it is a roller support, it won't allow any deflections or deformations perpendicular to the surface. Suppose here if I draw a line along the surface, this surface is along which direction? It is lying along X or it is lying along Y. See the representation, I have changed the representation here. Previously I have considered this is my X direction, but now I have changed it. So always we should not go blindly. So that's why I have interchanged the directions of the plane that we are talking about. So here my parallel surface is X. What is my perpendicular direction? Y. As you can see the direction of the rollers, they can freely move along X direction, but it won't allow any deflection along Y. So that's why in this case, the reaction force will develop along Y direction. Clear? Any doubt? So that's why I told you, if you are looking at the problem, you should always talk about with respect to the reference planes. Then the problems will be very, very, very clearer. So don't answer it blindly, okay? Let me draw one more kind of way. What about like this? Imagine that I am representing with X and Y. What do you think the forces are developing from? In this case and in this case, it is very much clearer, isn't it? In this case, the force will develop in Y. In this case also, the force will develop in Y. What about in this case? In which direction the force will develop? Is it truly along X? Is it truly along Y? One more thing. Yeah, Hari, did I give you that
Normal
this
to
angle 45 degrees?
normal to
Did I give this angle 45 degrees? I didn't. So that's why your answer is completely wrong, 45 to X. As we can say, perpendicular to the surface, let us say this reaction is R. If it is the angle is theta, so the direction is depending upon this theta. Okay. Now tell me, in this case, let me change some modifications here. Let us say here I'm taking X, Y. So if I'm talking about this example, which deflection is 0? For this, the criteria is this, the reference plane is this. Which deflection is 0 which deflection is not equal to 0? Anything you can ask.
Why?
In this case, the deflection along Y is equal to 0. In this case, which deflection is equal to 0? You can see, I have changed these reference planes again.
X again.
I can say deflection along X equal to 0. What about in this case?
The direction perpendicular to the resultant direction, the deflection.
Yeah. So here, if I'm specifically talking about with respect to X and Y, I cannot completely say that delta X is equal to 0, delta Y is equal to 0. That means deflection Suppose if I talking about, see, let us say this point is A, and this is the surface you are talking about. Imagine that this point has moved to somewhere here. This is point A initially, and this is the point B. That means if you are talking about inclined surface, delta x is also possible, delta y is also possible. That means these are not completely zero. If I'm talking about the deflection along the parallel to the surface, I can say this is what my deflection. If I resolve it into the directions along x and y, I can say delta x and delta y. So if rollers are completely lying along truly horizontal or truly along vertical, then we can say one of the deflection component is equal to 0. But if it is along the incline, then deflections along x and y, those are possible. Okay. Similarly, let us say if we are talking about fixed support, the name itself we can understand, isn't it? Fixed support, that means it won't allow anything, any type of deformation. It won't allow either translation, it won't allow any rotation. So if it is a fixed support, I can say at that point delta x is equal to 0. If I'm talking about these are my planes, delta y is equal to 0, and also it won't allow any rotations. Theta z is equal to 0. So it won't allow any deflections along x equal to 0. That's why it will generate the force along x, resisting force along x. Similarly, it won't allow any deflection along y. That's why it will, resisting force will develop along y. Similarly, it won't allow any rotation along z. That's why the movement will generate. This is what if we are talking about two-dimensional plane. What if we are talking about three-dimensional plane? If we are talking about the same fixed support, if we are talking about three-dimensional plane, then how many deflections or translation are 0?
3.
Delta,
6.
delta x equal to 0, delta y equal to 0, delta z
Deflection.
equal to 0. Similarly, theta x 0, theta y 0, theta z equal to 0. Right. So total corresponding to these 6 types of, then there will be 6 resisting forces will develop. Now, is it clear about the resisting forces for traditional cases like roller support, hinge support, and fixed support? Fine, right? Just a second. As of now, any doubt? I don't think we have discussed very basic kind of questions. So let me know if you guys are having any problem with this. If not, then we can go to the next. Are you guys able to see this chart, meeting chart pop up or not? You guys are only seeing the screen, right?
Yes, sir.
Yeah, okay. As I can see the pop-up of meeting chart, that's why I'm asking you. So it won't disturb you. Okay. Next. Let me come to the traditional problem. As of now, I haven't discussed about what is determinate, what is indeterminate. As of now, nothing. As of now, we have discussed about in which plane, which type of deformations are possible, and in which plane, which type of resisting forces are possible. That's what we have discussed about as of now. Okay. Now, one more thing we have to discuss about is whether my structure is stable or not. How do we define that my structure is stable. You might have heard, right? Stable, unstable. Can you tell me on what basis we are judging that the structure is stable? DS formula. Okay, don't tell me with respect to formulas anything. Forget about formulas. Have we discussed any formulas as of now? Even for the next class also, we don't discuss any formula at all. Forget about formulas, nothing. No formula. Any idea? Imagine this is what the structure that I have built, okay? Not exactly zero moments, sorry. That's not how we should say. We can't say exactly zero moments. Let us say this is my portal frame, two-dimensional portal frame I'm discussing you about. And let us say that wind load is acting here. Imagine, always, right? If imagine a building and wind load will act. Obviously, if you are analyzing for wind loads or if you are talking about earthquake loads, all the lateral forces will act at the beam column joints. So here the beam column joint is here. So imagine that either wind load or simply I can say lateral load is acting. Can you tell me how this structure will behave for this wind load? Will it resist or it won't resist?
It
See the
can't
complete
resist.
structure and let me.
It can't resist, sir.
Why so?
There is a movement along the wind direction, sir. There is no
So-
restriction along with the direction.
Yeah, what is the type of movement we will call about? In this case,
Movement,
the same structure is moving. That means we will call it as a rigid body motion, isn't it? If rigid body motion is possible, that means what is happening? The structure is simply as it is moving to some other place or some so and so. So wherever the rigid body motions are possible, then we can say that the structure is unstable. If rigid body motion means the resisting forces are not developing at all. As you can see here, this is the roller support. This is the roller support. If I apply some force, what will happen? It will simply move along the direction of the force without resisting it. Right? So if you want your structure to be stable, then you have to restrict which type of motions?
Horizontal.
You should restrict the rigid body motion, right? In this case, how can I restrict the rigid body motion? Let us say here my reference plane is X and Y. Here my rigid body motion is happening along the X direction, isn't it? Then how can I stop the rigid body motion? This is what we will say physically. If you want to talk about with respect to the formula, then what we can say? What is the Newton's third law? Do you guys remember? I think this is very easy, right? Newton's third law. As of now, the people very much remember this. What is the Newton's third law?
Every action has an equal and opposite reaction.
What about second law? Okay, forgot about it. So imagine in the place of roller, what if it is a hinge support? Is it stable or unstable?
stable.
Why? Because
The wind force is taking care of wind joint.
yeah,
Wind
rigid
joint
body
along
motion
X
is
direction.
rigid body motion is not possible here. So I can say what can be the resisting force amount here?
The same
If it is
magnitude
a
of
P,
wind force.
then the resisting force is equal to P. So in this case, for this specific problem, to avoid the rigid body motion along the x direction, to avoid the rigid body motion along the x direction, if I can say my sum of forces along the direction is equal to 0, as you can see here, it is P on the right, it is P on the left. If we add these two, how much will get? 0. That means if sum of forces along any particular direction is equal to 0, then in that case, rigid body motion is not possible. The best example you can say, if I am taking any object, if I apply forces like this in two opposite directions, what do you think the object will move? This will talk it as a conventional compression problem, right? Similarly, if I don't want any rigid body motion along the y direction, then what is the condition my structure should satisfy? If I don't want any rigid body motion along the y direction, then my summation of forces along the direction should be equal to 0. Similarly, if I don't want any rigid body rotation, that's what, right? If I'm talking about 2D, how many rigid body motions can be possible? Along x can be possible, along y can be possible, and rigid body rotation can also possible. How can I avoid the rigid body rotation? By making sure that my summation of moments along the direction will be is equal to 0. Now you guys know what are these equations are called? Equilibrium equation. So for the structure to be stable, we have to avoid the rigid body motion. How can we make the rigid body motion restricted? By making the summation of the forces along the possible directions will be equal to 0. Why I have taken only 3 here for the two-dimensional object? If it is a two-dimensional object, 3 types of motions are only possible, right? Along x can be possible, along y can be possible, and also rotation can be possible. So if I can able to avoid these 3, then my structure can be stable. So that's why these are called the equilibrium equations. Similarly, if I talk about the object which is in YZ plane, what can be my equilibrium equations? If my object is in YZ plane, I have to avoid the rigid body motions. So what are the rigid body motions? Along y, we should not allow. Summation y should be equal to 0. Along z also we should not allow. Summation fz is equal to 0. And also we should not allow any rigid body rotation. That's why summation of moment along direction
X.
x is equal to 0. Similarly, if we are talking about 3-dimensional plane, so if we're talking about a structure which is in 3-dimensional, that is how the reality works, right? Whatever the structure you take, it is in 3-dimensional plane. So how many rigid body motions are possible here? 6. To make it stable, we should not allow any rigid body motion along x. That's why summation x equal to 0. We should not allow rigid body motion along y. Summation y. We should not allow any rigid body motion along z. Summation z. Similarly, we should not allow rigid body rotation along x. Summation moments along x. Not allow rigid body rotation along y. Summation y. Similarly, should not allow rigid body rotation along z. So how many equations we are having if we are talking about an object or if we are talking about a structure in 2-dimensional plane? First criteria is that if you are talking about a structure, it should be stable. If it is stable, then rigid body motion should be avoided. How can we make it avoided? By making the corresponding forces is equal to 0. That means in your hand, if it is a 2-dimensional problem, then obviously in your hand, how many equations are you having? You are having 3 equations. If these 3 equations are only satisfied, then only your structure will be stable. So if you're talking about any two-dimensional plane in general, you're having three equations corresponding to the plane. Similarly, if you're talking about three-dimensional plane, how many equations are you having? 6 equilibrium equations you are having. For one more point, tell me what is the point of writing these equations? What is the use of writing the equations? Why should I write these equations first of all? What is the use of these equations in analysis part? Now for this, I should go to the linear algebra. Let us see if we are having two unknowns. I'm having two unknowns x and y. To get these two unknowns, how many equations I should have?
2 equations.
If I'm having two unknowns, then obviously I should have two equations. They can be in terms of x and y, like 2x plus 3y equal to 50, or 5x plus 2y is equal to something 20. Right? So if you are having two equations, if you are having two unknowns, and if you are having two equations, can you solve it or not?
Yes, sir. Possible.
So that's why in this case, in the terms of linear algebra, then I can say this as exact solution is possible. You guys might have remembered exact solution, infinite number of solutions, our solution is not possible. But in the terms of our analysis, we will call it as a determinate structure. Why? Because if how many equations we are having, if you're talking about two-dimensional structure, already in our hand, we are having three different equations, isn't it?
Yes, sir.
By using those three equations, up to how many unknowns I can solve it?
2 unknowns, sir.
3, sir.
So if you're having
Three.
three equations, you can solve three unknowns.
Yes,
So if you are talking about two-dimensional problem, and if you are having the three unknowns, then these three unknowns can be solved by using the equilibrium equation. So that's why we will call it as a determinate. That means we can find out the number of unknowns by using the equilibrium equations itself. We don't need to go and trying for another equations. Okay. Suppose in terms of linear algebra, let me tell you, I am having only two unknowns, x and y. And let us say 2x plus 3y equal to 40, 4x plus 5y equal to 20, 6x plus 9y equal to 60. What will happen? Can you tell me? I'm having two unknowns, but I'm having the three equations. What will happen? Do you really think, can I get the exact solution?
No, sir.
Why? Because in this case, what is happening? Number of equations are greater than the number of unknowns. That means if I solve these two equations, I'll get one xy value. If I solve these two, I will get one xy. If I solve this and last, I can get one xy. Which xy I should consider? This one, or this one? No, right? So in this case, what is happening? Your number of equations are greater than the number of unknowns. So in this case, you don't have any exact solution. You will say that you have infinitely many solutions. That practically we don't see in while analyzing the structure. I will tell you later on what basis. Similarly, if I'm talking about three-dimensional structure, if I want to classify my structure as determinate, up to how many unknowns I can say it?
6, sir.
6. That means if we're having 6 unknowns, these 6 unknowns I can solve it by using the 6 equilibrium equation. If it is a 2D, I can call it as a determinate when my
3.
unknowns should not be more than 3. Those 3 I can solve it by using the 3 equilibrium equations. As of now, it is clear,
Yes, sir.
right? Let us briefly discuss about the equilibrium with respect to 2-dimensional. Let us say, you all know that this is a determinate and stable, isn't it? Do you guys agree or not? Determinate and stable?
Yes, sir.
How many reactions will develop here?
True.
Let's say this is, let us say X, Y. Let us say this is F here. How many unknowns we are having?
3.
It's 1, 2, 3. These 3 unknowns I can solve it by using 3 equilibrium equations. What are they? Summation of X,
Summation of
Y, and also summation of moment is equal to 0. See, these 3 equilibrium equations, I have applied it for the entire structure, isn't it?
Yes, sir.
Entire structure I have taken, and I am looking about these 3 equations, right? And also one more thing you guys should identify, or you should understand, that wherever you're talking about the equilibrium equations, or wherever you're talking about the stability of the structure, stability is not always limited to the global point of view. Global means entire structure. Even if you take a component of a structure, it should be stable. Do you guys agree or not? Let us say that if I am having this structure, let us say these are all components. Component 1, component 2, 3, 4, 5, 6, 7, 8. Okay. So my entire structure is consisting of 8 components. If my entire structure is stable, that means if I take the entire structure and I can work out it for 3 equilibrium equations, summation of X, summation of Y, and summation of moment. Even if you take any one component of the structure, that means if I take the component 1, it should also be stable, isn't it? If entire structure is stable, then obviously each and every component in the structure is stable. If each and every component is stable, then for each and every component, the equilibrium equations will be applicable. Do you agree or not?
Yes, sir.
What is the statement I made? If entire structure is stable, for your entire structure, it should satisfy the equilibrium equations. In the same way, if your entire structure should be stable, each and every component should also be stable. If each and every component is stable, then each and every component should satisfy the equilibrium equations. That means even you take the entire structure, even if you take any component, or even if you take a single point from the structure, it should be stable. If it is stable, then equilibrium equations must satisfy. So my point here is that you take any point, or you take any element or component, you take any part of the structure, that should satisfy the equilibrium equations. If it is not satisfying the equilibrium equations, then it will not be the stable structure. So here either I can take a single part or single component, or I can take half of the part. That should satisfy the equilibrium equations. Why? Because it should also be stable. Any doubt regarding the application of the equilibrium equations?
No, sir.
Regarding the determinacy in a general sense? Yeah.
Sir, can you explain the 17 and 8 side, the 8 side, sir?
Can you please type? I could not able to hear you clearly.
Okay, sir.
Guys, as I'm telling you, if you're having any doubt, even if you're having doubt in positive, negative, you should stop me. Why? Because we'll go very slow for 1 to 2 lectures or 3 to 4 lectures, but later on, after we build up enough basics, then we won't go in this space at all. I'm telling you, within 1 second or within 10 seconds or within 1 minute, we must solve the problem. Yeah. Okay. So if you are talking about, I'm going again previously linear algebra case. Depending upon the number of unknowns, and also depending upon the number of equations, we will decide which type of solution it will exist. Let us say we are having 2 unknowns. In the first case, let us say if we are having 2 unknowns, y and z. To get an exact solution, your number of equations should be equal to number of unknowns. So as I'm having 2 unknowns, definitely I should have 2 equations to get the exact solution. Let us say, what happens if I'm having only 1 equation? I'm having 2 unknowns, y and z, but I am having only 1 equation. Can I solve the system? Can I solve those 2 unknowns, y and z?
Not possible to solve.
Not possible, right? To make it possible, what we can do? If only 1 equation is possible, we don't get any solution for y and z. So we should need how many additional equations? We need 1 additional equation. Why? Because we are having 2 unknowns, 1 equation we already have. So if you can get any 1 additional equation, then by using these 2 equations, then we can solve these 2 unknowns. What happens if we are having 3 equations? What will happen? Just like in this case, you are having 2 unknowns, but if you are having 3 equations, what is happening? These 2 either you can find out by these 2, or you can find out by these 2, or you can find out from this and this. That means we can have different types of solutions. If different types of solutions are possible, then that is not exact solution. So that what we call it as infinitely many solutions. In terms of stability, we will say it as a unstable structure. So these first 2 equations, whatever we are talking about, if number of unknowns are equal to number of equations, this case I will call it as a determinate. But in the second case, what is happening? I need additional equations. So that's why indeterminate. Why? Because by using equilibrium equations itself, I cannot find it out. I need some more equations. So that's why this is called the indeterminate. But in this case, we are having number of equations or more. That I will tell you by example. Let us say, in this case, if my structure to be stable, how many it should satisfy the equilibrium equations? How many equilibrium equations it should satisfy? For this structure to be stable, if I'm talking about 3, right? Summation of x0, summation of y0, and also summation of moment 0. Now come to the problem. How many reactions will exist at point A?
One, sir.
What is it? Let us say force along y at A. Similarly at B,
Force along at
1. That means how many unknowns I am having?
2.
2, sir.
But how many equations I am having?
3, sir.
Can I get the exact solution here?
No, sir. Not possible.
So that's why in this case, I will call it as a unstable. Can you make it as a stable?
Yes, sir.
Can add one, sir. One addition.
I don't want to change the support conditions. Still, can you please judge on what possible case it can be stable case? Let me tell you. Let me explain you. This is a very good example. Let us say. Sorry. Can you tell me why it is unstable?
3 equations to unknown, sir.
No, forget about the number of equations. The number of equations we have already seen, right? Why it is unstable?
It's a
Look at the problem and tell me.
Only translation, sir.
rigid body
Imagine.
movement.
Yeah. If I apply a force along x direction, what do you guys think will happen to this problem? What will happen? Will it be stay there or will it move away?
It will,
Sir,
Will it move away, right? Now forget about fx. What happens if I apply a load like this? Now tell me. Now I'm applying forces along y direction. Will it allow any deflection?
it can resist, sir.
resist, sir. No.
It will resist. Similarly, it will allow any deflection? No.
Oh, sir.
In this case, can I say it as a stable?
No.
If only one direction force, it is stable, sir.
Yeah, that's where we have to be very clear about. So, in a generic sense, see, if I'm talking about specifically about this problem, did I mention any direction of the force in this case? Did I say whether it is x direction force, y direction applied force? Did I say any movement? Did I? No. That means if I'm not representing any loading, it can be possible along x, the load can be possible along y, the movement can also be possible. So, if loading is not mentioned in the given question, that means you have to analyze for all possible cases. What are the possible cases for this case? The load can act along vertical direction. The load can along vertical direction, so horizontal. The movement can act. Because of this vertical and because of this movement, it might be stable. But what about because of this horizontal? It will simply move away. So, if loading is not mentioned in the given problem, then we have to think in a generic way. That means just like the way here we have discussed. But instead, if the load is given like this, then you should not think about generic way. You should stick to the direction of the loading. Okay. Is this clear? First of all, for the generic sense, is it clear or any doubt? I will discuss in detail in next class. Okay. Don't dump all the things on our mind on today itself. Okay. I think, or I hope this is clear for you guys. And coming to the stability part, just like our body, if we are healthy, each and every organ should be healthy. If any one of the organ is not healthy, then we are unhealthy, isn't it? Anything. So just like the same thing, if I'm talking about this. So if I'm talking about the structure like this, if entire structure is stable, then you should think each and every component should be stable. That means if I talk about what are the components here, I can say AB is one of the component. It should be stable. And BC is also one of the component. It should be stable. Or even you take any single part of the structure. See, I cut somewhere in between like this. it should also satisfy the equilibrium equations. So blindly or just stick to your mind that if you take any part or if you take any section, if you take any component, that should also be stable. If it is stable, then it should satisfy the equilibrium equations. Let us say if this is unstable, let us say if I am saying AB is unstable, do you think my structure is stable?
No, sir.
No,
Okay.
sir.
Oh, that is obvious, right? If I'm talking about my entire structure is stable, then everything should be stable. Each and every component should be stable. If each and every component is stable, if it is stable, it has to avoid the rigid body motion. If it is avoiding the rigid body motion, it should satisfy the equilibrium equation. So that's why you take any component, you take any part, anything, that should satisfy the equilibrium equations. Why I'm telling is that this is very, very important part, this stability part, this part. You can take any section randomly, you can take any part randomly, that should satisfy the equilibrium equations. There is no doubt about it. As of now, any clear? Any doubts? So, are we clear about determinate and indeterminate?
Yes, sir.
Even though we haven't solved any problems, but in the physical sense. You guys know about free body diagram, right? Can somebody tell me what is the free body diagram or how to draw a free body diagram?
The diagram which shows the action and reaction in the whole.
Yeah, thank you. And why it should be necessary for us to draw the free body diagram?
For getting equilibrium equations, sir.
Yeah. Let us say there is some object like this. Okay. So I'm drawing very bad pictures, so please don't mind. Okay. Let us say there are some loads, UVL loading, UDL loading, different types of loads that may be acting here. So in a physical sense, we know that if it is to be stable, rigid body motion should be avoided. This is how we convey it through words, isn't it? But how can we quantify it? If you want to quantify it, you have to express in terms of mathematical equations. That's where we are talking about equilibrium equations, Fx0, Fy0, and also we are talking about Mz0. So if you're directly looking at a structure, will they be visible on the structure itself? No, right? So we have to represent them. Wherever there is a possibility of applied forces or wherever there is a possibility of reaction forces, we have to represent those forces and then we have to understand them, whether they are getting equal to 0 or not. So that's why the heart of the problem for structural analysis or even for engineering mechanics is that free body diagram. Very, very, very important. Free body diagram. Okay. Now, let me tell you how we can solve. Let us say there is a beam AB. For the beam AB, at A, I have placed a in support. At B, I have placed a roller support. Okay. Now tell me, I want to draw the free body diagram for the beam AB. So the first, sorry. So if you want to draw the free body diagram, the first thing is that for the beam AB, take it away from all the contact points that the beam have. So if I'm talking about the beam AB, at how many points it is contacted with? In this case specifically, at A, it is connected with hinge support. At B, it is contacted with roller support. So first of all, I will remove those supports and I will draw the beam as it is. So the first step is that for whatever the part you want to draw the free body diagram, remove it or untie it from all possible contacts it is having. So in this case, at A it is having hinge support, at B it is having the roller support. Okay. Now, after that, you have to represent the action of the surface or action of the contact point on the beam. So what is the action that in support it is creating on point A on the beam? This hinge is not allowing any deflections. That means it is imposing the resisting forces at point A. So what is the effect of having hinge support at point A is nothing but the forces. We have already seen if it is a 2D case, two forces will exist in this case. The force along y direction, the force along x direction. Remove it from the all possible contacts and then show the effect of the object in terms of the forces. So here, as it will not allow any deflections, it will impose the resisting forces at point A. That's why instead of representing it as a hinge support, I am representing in terms of the resisting forces. Okay. Now, similarly at point B, I am reviewing this roller support. What will be the effect of roller support on the beam at point B? It will not allow any deflections perpendicular to the surface. In this case, it is vertical direction. So that's why I will show the resisting force reaction at point B. So this, I think we might already know, right? Very funda or very basic problem. Isn't it? Now, let us say, before that, is it mandatory that I should represent the force? Let us say if I'm talking about force Fy, is it mandatory that I should represent only along upward direction? Is there any such kind of rule? Here also I am representing Fy along upward direction. Is there any such kind of rule that I should apply the force upward only, resisting force? No, not at all. These are nothing but resisting forces. Their direction will always be opposite to the direction of the displacement. So it is, we kind of habituated to represent like this. Okay. But instead, it's not. You can represent it in downward, you can represent leftward, you can represent it like you wish. Okay. There is no hardened rule about it. Okay. Suppose if I want to draw free body diagram of AC, can you tell me how can I represent it? First of all, I will represent the part AC. And then at A, I already have shown you upward force will develop and also horizontal. What about at C? Do we have to represent any forces or it will be free kind of a support?
Free.
Do we have to represent any forces at point C or not?
Not, sir.
No need to represent?
Yes, sir.
So is it hinges, sir?
We may, whoever voice is not able, they can type, sorry.
So it's a fixed support.
First question, Do we have to represent forces at C or not?
Not, sir.
No need to represent. One, any other answers? Everybody satisfied with that answer? Or anybody want to contradict the statement? You guys can free to.
Have to mention it, sir.
Why? If so, why?
If it is hinges, it means it we have to mention it.
See, A and B are external supports, okay? And
Okay, sir.
wherever we are separating a point or wherever we are breaking an element into two, always there will be contact forces. You guys might have heard it. What is the definition of contact force? So if you are talking about AC, or if you are separating, let me erase this and write down, okay? It will be clear. So wherever you are separating or wherever you are breaking at a point in an element, always you have to represent the contact forces between them. Those are called the internal forces. These are called the resisting forces because of the supports. And wherever you are breaking in between a surface, not only here, you break any surface, you have to represent the contact forces at that point. Here, again, I'm telling you, it is a 2D problem. So how many contact forces may exist? Again, the answer is 3, always 3. Even if I talk about deflection, 3. If I talk about contact force, also 3. So there might be a contact force that will act along X direction. There might be a contact force that might act along Y direction. I kind of habituated to Fx and Fy. Okay.
Rotation.
And also there might be a possibility of movement. So always remember that wherever you want to break a point in an element, or wherever you want to separate a point in a beam or anywhere, always remember that you have to represent the contact forces at that point. So this is what for the beam AC. What about for the part CB? What will be the direction of force along X direction at point C?
3, 6, Fx, Fy.
Here I will say that I will represent it along the X. Why? Because join these two again. If you join these 2 points, contact force acting on the right side, here contact force is acting on the left side. If you add those 2, then what will happen? Positive and negative will be equal to 0. Similarly, in this surface, contact force I have represented along upward direction. So what is the contact force direction I should represent this point?
Opposite direction.
Direction Y. Here movement I have represented in clockwise direction. So what is the
Yeah,
contact force I should represent? Anti-clockwise.
Anti-clockwise.
If we again join all these things, do you have any applied force at point C?
No, sir.
That's why again, if we add the contact forces, they should come equal to 0. These are nothing but a contact equilibrium. That means wherever you are separating at a point, forces will exist at the contact point. Those are called the contact forces. And if we again join back them, it should satisfy the original condition. What is the original condition here? At point C, there are no applied forces acting at this point. That's why again, if we again join these T, it should be 0. Any doubt for the free body diagram for AC and CB? At A also, how many forces I'll have? I'll have one reaction, let us say F1, one reaction F2. So if I look into the free body diagram of AC, can you tell me how many unknowns I am having?
5, sir.
How many equilibrium equations I have?
3, sir.
That means how many unknowns I am having?
2.
Is it right? Is it right or wrong? It is a determinate, isn't it? Simply supported beam is a determinate problem or indeterminate problem.
Determinate problem.
Then how come we are having the additional unknowns too?
Sir, equal and opposite reactions only at the point, right, sir?
But see,
Probably
these three
equal-
don't know. These three also we don't know. So first of all, what we will do is that we will solve it for the entire structure. Let us say F1, F2, and here let us say F3. This is point A, this is point B. If I apply the equilibrium equations for the entire beam AB, can I solve F1, F2, F3?
Yes,
If I
sir.
use summation of x equals 0, summation of y 0, and if I use summation of z equals 0, can I find F1, F2, F3? We
Yes,
can,
sir.
right?
Yes, sir.
So, for the entire structure, if I apply the equilibrium equations, I can get F1, F2, F3. After getting these three, now look at here, in this case. These two are known or no, unknown? F1 and F2.
Unknown, sir.
Known, because these knowns are coming from the entire structure. Now, how many unknowns we are having?
Only one.
These three. Now, this has become 3 minus
3.
3. That will be equal to 0. That means, how we have applied the equilibrium equations here? On what way we have applied? First, we have applied the equilibrium equations on the entire structure. And then we have applied equilibrium equations on the
Part
some
of
part, or we can call it as a
section.
Did you guys remember that in truss problems, you guys might have remembered the method of sections?
Yes, sir.
You might have remembered in method of sections, first you will find the support reactions based on the entire structure, and then you will take any one part of the section and then you will apply the equilibrium equations there. So this is what one example of this. Is it clear? Equilibrium application of the equilibrium equations for the entire system and the one part of the system. Any doubts as of now?
No, sir.
No, sir.
Clear, right? Now, let us talk about a last fundamental basic thing. What is scalar? I think you guys might have encountered with scalar, vector, tensor. I don't mind you guys telling me this, but please tell me about these two at least.
Only magnitude.
We are having only magnitude, right? What is the best example for it?
X, Y, Z.
What about the vector?
Magnitude from direction.
We are having the direction. And what is the best example for the vector? As of now, whatever we have discussed. If I talking about the force,
Yes, sir.
vector or scalar? Vector, right?
Vector.
Means,
Vector.
so wherever I am talking about, what about the movement?
Magnitude.
Movement, movement. Scalar or vector? It is also a vector, right? So,
Okay.
it is having magnitude. Let us say if I'm talking about the force, I can say it is a 10 kilonewton. Will it be sufficient if I say that force is 10 kilonewton? If I say to somebody that, let us say, there is a cantilever beam, and at point B, I am saying that force acting at point B is 10 kilonewton. Is it sufficient?
No, sir.
Why? Because I should tell you, right, whether it is acting in the downward direction, or I should tell you whether it is acting in a upward direction. So as we are dealing with the vector quantities, for us, it is mandatory to say with respect to the direction. Let us say, if I'm talking about single value, plus 10, upward 10 kilonewton or downward 10 kilonewton, I can say. But let us say, along line of action, let us say 10 kilonewton, 20 kilonewton, 30 kilonewton, 50 kilonewton. If I ask you, what is the net force acting along this direction? How much you will say?
40, sir.
Yeah, the answer can be anything. But my point is that while calculating, you will not write upward 10 plus downward 20 plus downward 30. Will you write like this? No, isn't it? So it will be very difficult for us to use the direction for calculation purpose. So that's why what we will do, we will assign some symbol. What is that symbol? Plus or minus. Why I am telling you this is that what are the students that I have taught to the previous batches are after starting the course or while during equilibrium equations or while solving some big problem, they will ask you why this minus, why this positive. Why? Because it is a vector. For that vector, every time it is difficult to represent the convention like upward 10, downward 10, upward 10, downward 10. So that's why what we'll do, we will assign some direction. Usually what we'll do, if I'm talking about the coordinate system, X and Y, what I will say that if any force is acting along the positive X direction, I will treat that force as a positive. If any force is acting along the negative X direction, that force I will treat as a negative. So if I'm talking about Fx, if I represent plus 10 kilonewton, or I can also represent 10 kilonewton right side. So instead of representing this right side symbol, I am representing with respect to this sign. So if I assume, this is also assumption. It is not mandatory that if it is along the positive X, you have to treat it as positive. It is not like that. You are solving the problem. At the end of the solution, you have to represent a magnitude. You have to represent a direction. For the calculation purpose, you have to take some direction specific to corresponding symbol. So here I am taking the symbol as positive if it is acting along the positive X. So according to me, if I'm writing plus 10 means, what is the direction I'm talking about? Right side. If I'm talking about minus 10 kilonewton, I'm talking about, according to me, I'm nothing but, I mean to say 10 kilonewton acting along left side direction. Just like the same thing, if I say positive force along y direction, then I can say, if I say Fy is positive 10 kilonewton, that means I mean to say that 10 kilonewton upward. If I say minus 10 kilonewton, I mean to say that 10 kilonewton downward. You can consider it in reverse direction also. There is no hardened rule. It's up to you. But at the end of the day, after summing the things and do some calculation part, you have to tell me the final net magnitude and final direction. So that's why don't always get confused with the positive or negative. That we can consider according to our wish. It's up to you how you are comfortable with. Okay. We'll solve some more problems based on this. As of now, any doubts regarding the sign convention?
No, sir.
Or anything about the today's class, let me know. Today we have just discussed about equilibrium equations and what is determinacy. And yeah, I think that's it, right? If you have any problems or if you have any doubts, as of now, let me know. If not, we can end up the class now.
Sir, can you show the first two slides, sir?
First,
Two slide. Before one, sir.
hmm?
Second one. Second and the third one. Yeah. Okay. Sir.
Once again, I'm telling you, asking doubts is very much important for the first few classes because we are going to build up the basics. If basics are not clear, then we will be thrown away from the understanding the concepts. So the basic equations are equilibrium equations and what is determinacy, where to apply. As of now, we haven't solved how to find out the determinacy and all that. We will continue in the next class. If not, if you don't have any doubts, then we can wind up the class.